Ever been stopped at a traffic signal and all the turn signals in front of you are blinking at different rates and you're watching to see when they synchronize? Hey, turns out you're doing math. So I've put together a couple of numbers here. They're not prime numbers. In fact, I put them together so I know what they factor into. What I'm going to do is make a little table here that shows the possible factors they could be. 2, 3, and I jumped to 5 because remember, when we're doing factoring, when we factor all the way down, we can factor all the way down to prime numbers. So I don't include the non-primes in here. I have 2, 3, 5, 7, 11. I'm not going to 13 because once again, I made those numbers. I know there's no 13 in them. So let's go ahead and factor them. We've got 2100, 2100. We know it's even, so we know it divides by 2. So we divide this by 2 and we get what? 1050. So 1050. Now, 1050 is also even, so we know it is divisible by 2. So we divide this by 2 and we get what? 525. And so we know we've got 1, 2 2's in there, right? Now, doesn't factor by 2 again because 5 is not an even number, so we then go to the next prime number. Is it divisible by 3? Well, the way we figured out whether it was divisible by 3 was we added all the digits of our number together. So 5 plus 2 plus 5, that's 12. 12 is divisible by 3, so we know that 525 is also divisible by 3. If you didn't realize that 12 was divisible by 3, then 1 plus 2 equals 3. That's divisible by 3, right? So we go to 525 and divide it by 3. And what we get is 175. And so we know that there is 1 3 in there. Is 175 divisible by 3? 1 plus 7 is 8, plus 5 is 13. 13 is not divisible by 3, so we're done with our 3's. Now let's move on to 5. Does it end in a 5 or a 0? It turns out it does. So 175 is divisible by 5, and when you divide it by 5, you get 35. So there's a 5 in there. Is there another 5 in there? Well, ends in 5, so yes. So 35 divided by 5, that's equal to 7. So we had a second 5 there. And it turns out the other or last prime number is a 7. So we've factored 2100. Let's factor 4312. 4312 is divisible by 2. How do we know that? It ends in an even number. So we divide that by 2 and we get 2156. Now, 2156 turns out that's divisible by 2 also. How do we know that's divisible by 2? 6 is an even number. So 2156 divided by 2 is 1078. 1078 is also divisible by 2. So we divide that by 2 and we get 539. All right, so we've got 1, 2, 3 2's in 4312. Is 539 divisible by 3? Well, we do the same trick we did before. 5 plus 3 is 8, plus 9 is 17. 17 is not divisible by 3, so there are no 3's in it. 539 also does not end in a 0 or a 5, so we know it's not divisible by 5. But is it divisible by 7? Well, the way we do this, there was a trick we did in the last lesson, which showed us that if we take the last digit off this number, we're left with 53. And then we subtract twice the digit that we pulled off. So minus 2 times 9, which is 18. That's going to give us 35. Is 35 divisible by 7? Well, it turns out it is. But let's go ahead and apply this rule again. And we've got 3 minus 2 times 5, which is 10, which gives us negative 7. The negative 7 is clearly divisible by 7. So we know that there is at least one 7 in it. What is 539 divided by 7? Well, it's equal to 77. 77. This one looks a little bit easier, right? So 77, that looks like there's another 7 in it. We pull a 7 out of 77 and we get 11, which means there is an 11. All right, so we've got these factored. Now that we've got them factored, we can take a look at 2 new topics. Now, the first topic is called the Greatest Common Divisor, sometimes called the Greatest Common Factor, but I'm going to abbreviate this GCD. All right. Now, the greatest common divisor of two numbers, and I'm going to go ahead and give you some right now. We'll just say A and B, and it's written GCD of A comma B. All right, so there's the nomenclature we're going to use. It is the largest integer C such that C divides A and C divides B. All right, and so what I want to look at is what's the largest integer that I can divide into 2,100 and that same integer divided into 4,312. Let's take a look at an example with values that are a little smaller than the two I've given here. For example, what is the greatest common divisor of 30 and 18? Now, what I'm going to do is I'm going to factor these guys. So 30 is equal to what? 2 times 3 times 5. So 2 times 3 is 6, times 5 is 30. So those are the prime numbers that we can factor 30 into. What about 18? 18 also has a 2 in it. That makes it 9, and then we have 3 times 3. Now, we know that 2 divides both 30 and 18. We know that 3 divides both 30 and 18, but in the case of 18, we can actually divide it by 3 twice. We can only divide by 3 once whenever it comes to 30. So the only prime factors that 30 and 18 share are 2 and 3. So really what we've got is the greatest common divisor of 30 and 18 is equal to, well, they both have a 2, they both have 1 3. Only 18 has the second 3, and only 30 has the 5, so that second 3 and the 5 are not included in this greatest common divisor. And that's saying that the greatest common divisor, or the greatest common factor, is 6 in this case. So 6 goes into 30 5 times, 6 goes into 18 3 times, both of them having what's left over. Now, there's actually another trick that we can use whenever it comes to determining the greatest common factor. Well, that trick is called the Euclidean Algorithm. And the Euclidean algorithm is based on our old friend, n is equal to m times q plus r. In other words, I have two integers, and any two integers, and for any two integers, there is a unique q and r which satisfies this expression, where r is less than or equal to 0, and where r is greater than or equal to 0 but less than m. Now, the unique case when r is equal to 0 says that m times q, two integers times each other, equal n. That identifies q and m as being able to be divided into m. Well, let's write this a little bit different. In fact, let's write this with respect to the a and b that we're talking about whenever it comes to our greatest common divisor. So we have a is equal to q times b plus r. Now, if d is a divisor of both a and b, then what we've got is that d divides a. Turns out if d divides a, d also divides q times b plus r, right? This right side of the expression. Now, we know that all four of those are equal to integers, right? And so whenever I make the expression, whenever I divide this expression by d, whenever I divide q times b plus r and divide that by d, I know that the result is also going to be an integer. If we separated this fraction and got q times b divided by d plus r divided by d. I know that since d divides b, I've already said this, d is a divisor of both a and b. Since d divides b, then the division of b divided by d results in an integer, and you've got q times an integer. Q is an integer, so this bit right here is an integer. Now, r divided by d also has to be an integer since a divided by d is an integer. So on the right-hand side, or the left-hand side of the expression, we've got a divided by d. That's an integer since d divides a. Then we also know that r divided by d also has to be an integer. And as you divide and divide and divide, you realize that if you use d as the greatest common divisor, then what you're saying is the greatest common divisor of a and b is also the greatest common divisor of b and r. So let's apply this to our simpler expression. So if we have a is equal to 30 and b is equal to 18, what I'm saying is that 30, if we substitute into that expression, is equal to the greatest number of times you can pull 18 out of 30 is once. So you can have 1 times 18 plus, well, what happens after you pull 118 out of 30? You're left with 12. And so since the GCD of 30 and 18 is also the greatest common divisor of 18 and 12, let's go ahead and repeat this exercise. What we've got is 18 is equal to, well, how many times can I pull 12 out of 18? Turns out 1 time. So 18 is equal to 1 times 12 plus what's left over? Well, when you pull 12 out of 18, you're left with 6. So we also know that the greatest common divisor of 18 and 12 is equal to the greatest common divisor of 12 and 6. Starting to look a little more obvious now, isn't it? So we've got 12 is equal to, how many times can we pull 6 out of 12? Well, it turns out 2 times with a remainder of 0. And now that we've got this remainder down to 0, we know that this is a divisor of this. We know that 6 is a divisor of 12, which means, like we figured out before, the greatest common divisor of 30 and 18 is this 6. Now let's apply both of these solutions for coming up with the greatest common divisor to our larger numbers up here. The first one we did was we said, okay, what is the largest number of factors that we can take out of both of them together? So let's look at calculating this greatest common divisor of 2,100 and 4,312. Well, what is the largest number of factors for each of these columns that is shared? In other words, what's the most 2's we can pull out of both 2,100 and 4,312? Well, the maximum number of factors that we can pull out of both of them turns out is the minimum number for that particular prime number. And we have 2, which is the maximum we can pull out of both. Now, since 4,312 doesn't have any 3's, we don't pull out any 3's. Since 4,312 doesn't have any 5's, we don't pull out any 5's. There is 1 7 for both 2,100 and 4,312, so we can only pull out 1 7. And since 2,100 doesn't have any 11's, we can't pull out any 11's. Therefore, the greatest common divisor of 2,100 and 4,312 is equal to 2 times 2, the two 2's, times 7, which is equal to 28. So that's a real simple way to figure out what the greatest common divisor is out of those two numbers. But let's go ahead and take a look at the Euclidean algorithm and see if we can't figure it out that way. Now remember, what we're saying is we take the largest number, the 4,312, and we figure out how many times I can pull 2,000, the smaller number, 2,100 out of it. And it turns out I can pull it out 2 times. So there's going to be a remainder, but I know that I can at least pull 2 2100s out of 4,312. And what I'm left with is 112. And so I know that the greatest common divisor of 4,312 and 2,100 is the same as the greatest common divisor of 2,100 and 112. So I take 2,100 and I say, okay, I'm going to figure out how many 112s I can pull out of it. Well, by using a simple calculator, I can figure out that I can actually pull 18 112s out of 2,100. So 18 times 18 times 112 is up to, but not more than 2,100. And that leaves 84 as a remainder. So what is my greatest common divisor of 112 and 84? Well, 112 equals 1 times 84. I can only pull 184 out of 112, plus a remainder of 28. All right, so the greatest common divisor of 84 and 28 is the same as the greatest common divisor of 2,100 and 4,312. So we've got 84 is equal to how many times 28? How many times can I pull 28 out? Well, it turns out I can pull out 3 times with a remainder of 0, which means 28 is my greatest common divisor. Guess what? That's what we had calculated before, right? So our greatest common divisor, this guy, is equal to 28. Now, let's talk about a second topic. The least common multiplier. Now, this is, and sometimes I hear it said, the lowest common multiplier. I may swap it back and forth during this lesson. The least common multiplier of two numbers, and we're going to stick with A and B again, is the smallest. All right, the smallest integer again, such that, and we'll give this integer a name, we'll call it C, such that, and in this case, what we were looking at was, for the greatest common divisor, we were seeing the largest integer that would divide into both of these. And what we're looking at now is the smallest integer that both of these will divide into. So such that A divides C and B divides C. All right, let's go back to our example before. And by the way, this is typically written LCM of A comma B. All right, so let's go back to our simple example again, where A is equal to 30 and B is equal to 18. What we're looking at is how many times, what is the smallest integer I can multiply A by, and what's the smallest integer, different integer, that I can multiply B by in order to get them both at the same level. All right, let's make a little table for this. We'll just say, let's say 30 times 1 is equal to 30. 30 times 2 is equal to 60. 30 times 3 is equal to 90. 30 times 4 is equal to 120, and 30 times 5 is equal to 150. All right. Now, what we're looking at here, I just multiplied out a little bit. If I need more, I'll multiply more. But what I want to do is I want to just show, as we're multiplying 30 by different values, different integers, I want to see if I can get them to match 18. And so 18 times 1 is equal to 18, right? 18 times 2 is equal to 36. 18 times 3 is equal to 54. 18 times 4 is equal to 72. 18 times 5 is equal to 90. Now, do these at any point share a common value? Well, it turns out that 18 times 5 is equal to 90, and 30 times 3 is equal to 90. That's the first integer that they share in their sequence of multiplied values. So the least common multiple for 30 and 18, that's equal to 90. Now I want you to see something here. If you look at 30, 30 was 2 times 3 times 5. The only factor it was missing from 18 was 3. it had to have a second 3. And if you look, when we multiply 30 times 3, that came up with our least common multiple. The one element, the one factor that it was, the prime factor that it was missing from 18, if you multiply that times 30, you got the least common multiple. Let's go over on the 18 side. 18 was 2 times 3 times 3. The factor, the prime factor that it was missing from 30 was 5. When you multiply it times 5, you get 90. You get to the least common multiple. Let me make some space, and we'll do the same thing for those numbers. So the least common multiple of 2,100 and 4,312. Well, when you look at these two numbers, 2,100 is missing a 2. So in order to get it up to the least common multiple, we have to add that 2 in. And so we're going to have 3 2's. Now, in order for 4,312 to reach the least common multiple, it needs to have an additional 3 and 2 additional 5's. So 1 additional 3 and 2 additional 5's. The largest number of 7's, 4,312, has 2 of them, while 2,100 only has 1 of them. So we need to multiply that top one by an additional 7. When you look at the 11's, we need to have at least 1 11. And so the idea is we take the maximum number of prime factors, and that is what we're going to create our final product from in order to create our least common multiple. Another way of looking at it is saying that, one of these numbers, 4,312, what does it need to be multiplied in order to have at least, at a minimum, the same number, at least the same number of multiples of each one of those primes as is in 2,100. So this becomes 2 times 2 times 2, there's 3 2's, times 1 3, times 2 5's, times 2 7's, times 1 11. And when you multiply all of that out, you get 323,400. So 323,400 is the least common multiple of 2,143.12, which means basically that both of these numbers go into this integer without a remainder, and this is the lowest integer that satisfies that. Now let's do one more thing. It turns out, and if you look at this, what I've got is, if I were to multiply these two numbers together, if I were to multiply the A and the B together, I would have 5 2's, 1 3, 2 5's, 3 7's, and 1 11. If I were to multiply their greatest common divisor and their least common multiple together, I would also have 5 2's, 1 3, 2 5's, I would have 3 7's, and 1 11. So it turns out that, and in fact I've erased my value here, it was what, 323,400? All right. It turns out that if I multiply A times B together, that is the same thing as the greatest common divisor of A and B times the least common multiple of A and B. So let's try and see if that works out here. Let's take 2,100 times 4,312. And we're not going to do necessarily this equation. What I'm going to do is say, I'm going to assume that I've got the greatest common divisor. And so instead, I'm going to bring this into the denominator of the left side of the expression. And so I'm going to divide by 28. And what you do whenever you figure out this expression, 2,100 times 4,312 divided by 28, turns out you get our friend 323,400. Now, the greatest common divisor and lowest common multiple are used all around us. For example, you might use it to figure out what is the maximum number of like-sized objects you can pack into a packing container. You can use it to figure out what the optimal timing for traffic signals is along a long, busy street filled with traffic signals. Oh, and that turn signals, the blinking and the blinking of those left-hand turn signals, that's also least common multiple. What's the A and B? Well, it's the time between blinks.